Okay, we start up. So today I'm going to go through a little bit of your old course in fluid mechanics. I got some mail about Bernoulli and Bernoulli with losses regarding exercise 3. So I'll just quickly go through the theory there. I mean, it's stupid if you fail when you do a comparison and you have got the old classic Bernoulli wrong. I mean, that's not part of this course. We as a lecturer, we have a tendency to forget that we train you here at the university to learn things fast. When you have taken the exam, forget it as fast as possible so you have space on your hard drive for the next course. We have a tendency to forget that. So I know several of you are struggling with Bernoulli, so let's do that one first. Then I'm going to look a little bit into some tips and tricks when it comes to OpenFOAM. And we have to address very, very important stuff, verification and validation. Essential when it comes to a CFD simulation. So we will start with simple Bernoulli. Any questions from you before we begin? That's okay. Now I know the list on the homepage in Blackboard is not correct for the different groups. I haven't had time to adjust it, so I'll hopefully in a couple of days I will have it correct. Check it that it is correct, so when you deliver exercise 3, that the group is correct. If it's not, mail me, tell me. Okay, Bernoulli with losses. So what do we have? For the geometry, we have something like this. We have a pipe, and a bigger pipe, and a smaller pipe. Something like that. So yes, you have a diameter 1 and a diameter 2, and back to diameter 1. You have a length 1, a length 2, and a length 3. Here. And then we're sending in a constant velocity. Something like this. Okay. I've got a question from several of you. Can we do it like this, or should we use the trick we had from exercise 2, finding a fully developed flow here and send that one in? Then we can skip this length number 1 substantially. You can if you like, but no, I won't sort of insist on that one. That was exercise 2 anyway. So you can do it easy, send in a flat velocity profile. Then you need the Bernoulli solution, Bernoulli with losses, to have something to compare with. That's the only thing we have for this exercise. So you start by saying, what do we have at the inlet? Well, we have a pressure 1, if you like to call it that, by density. You have an alpha, and then the average velocity squared. And then you don't have anything else on the inlet. What's this alpha? Well, you're sending in a flat velocity profile. Alpha is 1. No problem there. Equals. And then you have to do this in several steps. You have to find what is the pressure here before you hit the expansion. What is the pressure here just after you have passed the expansion? What's the pressure here before the contraction? What's the pressure here just after the contraction? And then finally, what's the pressure at the outlet? So that means you have to do this several times. Say now, if we start here, if this is point 1 and this one is point 2, okay, I will have a pressure number 2 by density plus. And then actually we should write alpha 1, and now we have an alpha 2. And here the velocity is actually the same, average velocity half. And then you have the pressure loss, the major pressure loss due to viscosity. So here you will have a friction factor F, and then you will have the length by diameter, and then you will have the velocity squared half. I would suggest keeping Bernoulli on this form, not divide by G, so you have it as heads or multiply with density, because in OpenFOAM, remember, the pressure you are receiving when you are simulating incompressible flow, that's just pressure by density. So you have P over rho from OpenFOAM anyway. So just keep it like that. That's just beautiful. What's this F? Well, it's a mathematically perfect pipe. Smooth, so you don't need any Colebrook or Haaland equations to find that one. We don't have any roughness on the wall. So I would suggest you can use Prandtl. That's beautiful. 1 divided by the square root of F equals, never remember that one, 2 times log, not ln, should be log. And then we have, what do we have on the inside there? We have the Reynolds number, and we have the square root of F again. Reynolds number, square root of F. And then it was, what was it? Plus 0.8, I think. Minus 0.8. Yeah, you better look it up. I'm not sure if I remember that one. I mean, that's a simple one. Of course, not so simple to solve this one for F when you know the Reynolds number. A little bit implicit, so maybe you have to use F0 or something on MATLAB. Shouldn't be a problem. Yep.
Can we use the Blasius equation?
No, unless. What's Blasius? F, what's that one? Square root of 10, is it, or something like that? 0.316 by Reynolds number 14. It's something like that, isn't it? Yep. If your Reynolds number is here, so that one is quite limited. So be aware. But if you are in this range, then actually this one will match that one quite perfectly. So that's okay. That's okay. Say now, this was 0.2. If you go to 0.3, then what happens? Well, we need some more terms. We will have here pressure at 0.3, and then we'll have an alpha 3, and then we'll actually have here a U number 3. Because the velocity here is going to be quite different. The average velocity, remember, always average in Bernoulli. And we still have this term. When you go from point 1 to 3, you still have to pass pipe number 1. But now you will have the expansion loss as well. K expansion. You'll find recipes for those. Yeah?
On the right side of the equation, isn't that U2?
You mean these ones? Well, U1 and U2, what's the difference? You have the same constant average velocity in the pipe. Doesn't matter. So you can call it.
2 is the end of the first pipe.
Yeah, but I mean the average velocity here is going to be the same. It's incompressible. So U1, you can write U2 if you like, but they are equal from continuity. Yeah.
What is the value of alpha 2?
Good question. You better find out. That's your headache. What is alpha 2? Yeah, good question. Now, say now we have a pipe here. Symmetry line. Here, I now have a turbulent velocity profile. How does it look? If it's not too high a Reynolds number, he may look something like this. Something like that. It's not a parabola. Parabola would be laminar. And if it was laminar, fully developed laminar flow, then alpha is 2 in a pipe. So here, what should we guess? 1.1 or something? The alpha is the correction for kinetic energy. So normally we say it's fairly small. 1.05, 1.0, something, something, something. Low Reynolds number. Low Reynolds number. If you go to a high Reynolds number, how does it look then? These shoulders against the wall is going to be much, much sharper. So he's going to look something like this. I would say 1.01, maybe something like that. So this is for you to decide what should this alpha be, depending on your Reynolds number. And if you want to do it, say, more correct, what's the recipe for the alpha? That's 1 over area. And then you have to take an integral of your real velocity distribution scaled on the average velocity to the power of 3. So after you have done a simulation, yes, you can reevaluate this alpha and find it more precise. That's actually possible using the formula for the correction factor. So whether you just say 1.1, 1.01, okay. That's not important here, but you have to know what it is and how to use it. I would say the solution here, it shouldn't be too sensible to the values of these alphas. This term here and this one, remember you have a subtraction between these two terms when you're seeking P2 equals, and not much difference actually. So they are not so important, but I mean they still are present, and you will see it when you plot the Bernoulli solution. Playing with alphas, you see they differ a little bit. That was alpha. Let's see now where were we? We are here. This one has to be multiplied with what? You have the expansion, and now you are talking sort of a minor loss here over a sudden expansion. What's the rule? You should multiply with average velocity squared half. Which velocity? Which velocity? For both expansion and contraction, the rule is you take always from the smallest pipe, always the fastest velocity. Because these, empirical expressions that we have for expansion and contraction, they should also be valid if the diameter 2 goes to infinity. I mean, you have a pipe into a very, very big reservoir or something. Then the velocity 0.3 on average is going to be 0. Then this will fail completely. So it's always the fastest velocity. Okay? And then you can continue. So going to point 4, for instance. Okay, then you have to add what? Well, then you have a friction for this pipe as well. Term like this, different friction factor, length 2 divided by diameter 2, velocity u2, the average velocity here, and so on and so forth. So there you have your kindergarten material. Yeah.
What would you consider like low Reynolds number and high Reynolds number when you use the term?
Low Reynolds number, what should we say here? 5,000, fairly low. And a higher Reynolds number, well, you just add some more zeros here. I don't know how many you want. So You have to write it like this actually. We have low Reynolds number and high Reynolds number. You decide. Other questions? Okay, let's get rid of this one. So, what do we get in the end here from these calculations? Well, that's the only thing that you have to compare your result with when you do the simulation. And here you will get a figure. Say we start here, and then we have an x-axis all the way over here. Here we have the expansion, here we have the contraction. So you have a distance here, x or z or whatever you want to call it. Here you have the pressure given by OpenFOAM, P over O. How does it look? Well, typically at the outlet here, you're going to use 0 pressure. That's a typical outlet condition in OpenFOAM or any CFD code. When you're sending in something known, then you set zero gradient on the pressure at the inlet. But at the outlet, you fix the pressure. You need a reference pressure there. So we start with 0. And we go through this pipe here. Well, for Bernoulli, then we will just have a straight line to point number 5. So you have something like this. And then you have the contraction. That's a huge loss actually for a contraction. And the problem here is that you will typically, when the flow hits, you will make sort of a bubble here, a vortex inside, say, just after the inlet there. So the opening will sort of be artificially smaller. So that's what you call a vena contracta, when you push in a fluid in a sharp-edged pipe like that. And the loss can be substantial, meaning you have a drop from 4 to 5, which is pretty high, actually. Something like that. Then we have pipe number 2, the big one. Well, we have a tiny little loss there as well. The inclination of this line, that's just due to the friction, is going to be much smaller than you have here, depending on your choice of diameters, of course. But if D1 is much smaller than D2, yeah, we have something like this. So there you have the pressure at point 3. Then between 2 and 3, what's going to happen? You will actually have pressure recovery, because from 2 to 3, the velocity goes substantially down. Hence, Bernoulli says the pressure has to go up. So you will have something like this between 2 and 3. And then pipe number 1, yeah, should then be something like that. So there you will have sort of a rough sketch of the Bernoulli solution, and then on such a figure you plot your own simulated pressure variation and see how well it fits. Probably it's not going to fit perfectly, but I mean this is what we have to compare with. Yeah.
So we should calculate those points with the Bernoulli equation?
Exactly. You should make this figure depending on your choice of Reynolds numbers, diameters, length, and then you know sort of the correct answer. But remember, Bernoulli is a rough engineering tool, so plus minus 15%. We have to accept that one. So no, you won't hit it perfectly. And that's not the point either with this exercise. But if you have huge differences here, then you have something to discuss. Why? Well, we choose a bad mesh. We couldn't afford more cells. I mean, you could still explain it, So that's the point with this exercise. Show me that you have understood the theory, you know how the setup should be. You don't have to do it, but you have to talk about it. Yeah?
Can this graph be obtained in Paris?
No. No, I can't do it at least. Maybe it's possible, I don't know. But so I always extract the data from the simulation over to Windows, and then I plot it in MATLAB. That's my way to do it.
And that is the pressure, like the pressure file or in.
Yeah, you can do a say plot of a line along the symmetry axis here. That's actually okay, because the pressure is not going to change much over a cross section here in the radial direction. The pressure there is fairly constant. So if you just use the center line pressure, that's okay. I will accept that. Instead of, I mean, it's possible to calculate average pressure at every cross section here, but I mean, it's a hell of a job, so don't waste time on it. Doesn't really matter. One more important point. You have the effect of the inlet. Here you're sending in a flat profile. It takes some time before he develops into a fully developed flow. And there you find some different formulas there. How long is this entrance length before you have a fully developed flow? It can be pretty far, actually. So this entrance length, actually it's the boundary layers that should be growing and should then meet in the center, and when they meet, here you have a fully developed flow. And from then on, nothing else happens. So then you are in a fully developed region. And they call typically this length here LH, or yeah, no, LE, I think Chengel and Shimbala used, scaled by the diameter. And yes, it's very empirical formulas. I don't remember them even. You have to look it up. Some researchers, they say 10, independent on the Reynolds number. I won't trust that one. I would check it out. How do you check it? When whether your say length is long enough so that you have reached a fully developed flow. Well, for a laminar flow, typically here, if you send in something like this line here, that is say more or less the friction, not too much change in the alpha, but a little bit. But you may have a pressure distribution going something like this. So initially, yeah, a lot of things happen. I mean, you're sending in a flat profile, so he has to redistribute from a flat profile to a fully developed one, and that costs energy. So you have some additional pressure loss here. But then, if your pipe is long enough, yeah, you should get the correct, say, inclination here of the pressure loss. It should be constant pressure loss when it's fully developed. That's one check. Look at your pressure distribution along the center line. See that, yeah, it becomes fairly as a straight line. Here, here, and here. I want fully developed before he hits the expansion, before he hits the contraction, before he hits the outlet. So check your pressure distribution along the center line. Also, what you can do is to plot the velocity at the center line. Plot the velocity along the symmetry line here. How will he look? Well, for a laminar flow, you will start then with, say, 1, and then the center line velocity will end up in 2. So here you will have something going like this. And when he is flatting out, then you know the center velocity is constant, doesn't change anymore. Then you should be in this region, fully developed flow. That's the laminar one. All the way up to 2. What do we have in turbulence? Well, you have a lot of things going on here actually. So maybe he will look something like this. Something like that. So he has some struggle here initially before he develops the correct turbulence scales and everything. But yes, he should also level off the centerline velocity. Maybe not too high, depending on your Reynolds number, so maybe 1.2 or 1.1 or something. So you still have to struggle with that one. So that's a second plot user should check the centerline velocity. How will he behave as a function of x here? Check these one out. Definitely something you have to include in your report. Other questions? Yep.
How crudely should we define like a linear pressure gradient? Should we like plot it and show here is it exactly linear? Or is it like?
No, as I said, you have to talk about it. Show me that you have understood the theory behind this. You don't actually have to do it, just talk about it. So impress me. Other questions? Now let's see, where are we? Here we are. Ah. Okay, so I said, yes, this group list is not correct, not updated yet. I believe this list should be correct, so I will have a look at it and then update your group list accordingly. But please tell me if you have any changes here that you haven't told me yet. So please just send me a mail or tell me, then I'll fix it. And check it out before Friday then that this list is okay. Now let's have a look at tips and tricks in OpenFOAM. OpenFOAM tips and tricks. What do you know? Here we find it. I'll put this one out on the homepage later. This is quite nice actually. Tips and tricks in OpenFOAM. It's taken from a guy who is called Joel Guerrero. I think he's Italian. Good guy. He knows OpenFOAM very well, a lot of experience. So I'm going to steal a lot of his material. I've done so already. So here you have something that definitely you should be aware of. So let's have a look at this file. So he's a little bit careful here. Yes, it's his personal personal view, but I think he's fairly well experienced, so well worth listening to. So yeah, this is for later. You may actually on your computer have several versions of OpenFOAM installed. That's actually an option. So sadly, they update, well, maybe not so sad, they update OpenFOAM, say, at least once a year. So that's actually nice. So the OpenFOAM is rapidly developing. Yeah.
I was wondering about the exercise tree.
Yeah.
And when we are to set initial values for k and epsilon.
Yeah.
Because in the OpenFOAM user guide there are a couple of formulas, including turbulence intensity and stuff. Are we going to use that one or just small numbers?
When it comes to the input values you need for k, epsilon, omega, depending on your choice of a turbulence model, you have to play around with these values. Yeah, you can start with these recipes that you find, but they are typically designed for, say, external flows, not internal. So they might be very, very wrong indeed. So you have to try, get a solution, and then have a look. Does your inlet value for k, epsilon, omega overshadow whatever is happening in the rest of your domain? Then you have put in a way too high value. If it's too low, then, well, you will see in your solution then, you have a totally different value at the outlet. Should be fairly, as an average value, close to what you chose at the inlet. So you have to try and add a little bit to find, say, a decent value. In the end, you should also then check. You have a result. This is my final result. This is beautiful. And then you change your inlet k 50%, 100%. Does your solution change? Is your solution sensible to whatever you send in? If that is the case, you're in trouble. Then you have to hit it better, well, quite precisely. If it's not that important, well, then who cares? So it must be investigated. Okay. This setup here, I think this one is on a Linux computer. I don't think you can do that on, say, the Windows version that we are using, but well, it might be possible. Can be a little bit messy, so your choice. I won't go through everything here in detail, so this will be more things nice to know later on. The find command, we have played around with that one already, so yeah, very nice to know when you're looking for something. Looking inside the source code, we haven't discussed that one yet. I hope that we have time in this class to do some C++ programming, create your own version of a OpenFOAM executable. Everybody knows C++. That's good. So we'll see whether we can do that later. The Doxygen documentation, well, we haven't had that much use for it, and I don't think we will. Not so important. Yeah, so yeah, you have some rule here, and you have another rule. Never use Norwegian letters in your names, never. They should never been invented, that's the point. Running in a cluster or more than one CPU, not so important for us, at least not yet. The mesh and the mesh quality, this is quite essential, so we are going to look further into different meshes and how then to create a decent mesh. So yeah, you have the check mesh utility here. The boundary conditions, very important, of course. So yeah, this one we also have discussed. The initial conditions, normally you are only seeking a steady state solution. Maybe you're using a steady state solver like you're doing now with the simple foam. He doesn't use the time history at all. But if you are interested in time development, then the initial conditions might be crucial. Then the solution has to be correct at time equals 0, so that you have the correct, say, evolvement in time. Starting and running, yeah. Won't go through that one too much in detail. Discretization scheme. This is something I'm going to address also next lecture when it comes to verification and validation. Because the first step there is going to find out, have I solved my equations correctly? And then later you have to ask, have I solved the correct equations? That's two different stories. And yeah, you may choose some discretization schemes and then find a solution, and the OpenFOAM reports, yes, I have a converged solution. And the solution has nothing to do with reality, then you're in trouble. So you have solved the equation, but your equations are wrong. Your schemes are wrong. Bad idea. So you have to know what you're doing here. So here he has a sort of a setup. This might be a very, very good idea if you run into problems. You set up a simulation and it crashes. It won't converge. You can't get a solution. What the heck do you do? A dirty trick. You go into your numerical schemes and you change it to first order linear upwind. No, not linear upwind, just upwind schemes. This is a first order scheme and it's sort of illegal to use. It's only first order accurate and is way too diffusive. He includes a lot of, say, numerical viscosity, but he really dampens down, say, any sharp gradients, soften down your solution, but it's very robust. So this might be a good idea to start with something like this, just to get a solution. And then later you switch to more second order accurate scheme, and then you continue your simulation. You just go into your control dict and you say start from latest time instead of start from time 0. Then you can continue the simulation with higher accuracy. So that might be a very, very good idea. So here you have a second order setup for the these are the nonlinear terms in the Navier-Stokes. So you have so typically velocity times the gradient of a velocity, stuff like that, nonlinear terms. So here you have a linear upwind, so that's a second order accurate, and should be roughly stable. Not so stable as the first order upwind, of course. Even more accurate, but this may be a little bit unstable. Now you are talking central scheme, second order accurate, and that one can be very, very jumpy. So be aware of that one. But it's more accurate, still second order. So upwind, first order, linear upwind, that was central scheme. Just linear, also second order, he used several points upwind. And then you have TVD schemes, total variation diminishing, sort of will help down or get rid of over and undershoots in your solution. Yeah?
What does bounded and unbounded mean?
Bounded and unbounded, that means, say if you initially you have a jump in a quantity from 0 to 1. Then you see in your solution, before the jump he goes negative and then he goes beyond 1. Over and undershoots shouldn't happen. When it's bounded, he sort of force him stay between 0 and 1. And total variation diminishing does exactly that. This one is actually also a TVD scheme. He also gets rid of that one, but he will really smear out that jump, well, way too much. So he's too much damping, you might say, for this guy. If you just use this one, you can rapidly see that he's going to explode. So you get -10 and you get +20. Not bounded at all. So at the end of the day, we always want a second order accurate solution. Yeah. You have also some diffusive terms, the Laplacian, the second derivative. These are not so crucial. I would say it's a nonlinear term that is essential here. when it comes to instability in a simulation. But you may have a look at it. So you can play around with here numbers between 0 and 1 for the different schemes here as well. So we have some recommendations here, could be worth looking into. The details in all these schemes, we haven't looked too much into it yet. We'll see if we have time later in this course. I'm not so sure about that actually. Discretization. Yeah, this is something that we are going to address quite soon. When you have a mesh which is unstructured, then you don't have 90 degrees in your corners of your cells, maybe 45 or even worse. That's a problem. That's a problem. So what you call non-orthogonality. So that one is something we have to look into. Here are some tricks here about that one as well. So I won't go through this now. So here is the remedy when you have that sort of mesh, not 90 degree, but something else. 120 degrees, 150 degrees, or 30 degrees. You have this non-orthogonality corrector, and then you can choose some additional iterations to adjust for, say, such non-orthogonalities. Under relaxation, this also may be a trick to sort of save your simulation. It crashes, it's unstable. Well, then you soften down these, say, updating parameters. So here you have your old value, and then you have calculated an update. And then you use only 50% of the update. Don't take 100%. That also softens down, say, the iterative schemes. That may also save your simulation. So the different relaxation factors between 0 and 1. Yeah, the higher to 1, the faster you will find a solution, but it may be unstable. The stability, smaller, the more stable it will be. Well, I see we have time. I think I'll take a break here. Any questions? We'll continue with this one then after the break.